All right, so in this problem, we are trying to calculate the net force on a particle in question. We have two different scenarios or two different orientations of particles. In part A, we have two particles, 1 and 2, separated by a distance d of value 2.8 meters. Okay, so, well, let's do that one first before we worry about part B. Okay, so let me draw a quick free body diagram, if you will, of it. Okay, that's it. We have, I'll call it Q2 and Q1, separated by a distance d. Yep. Now let's write the force on the particle in question. So in part A, we want to find the magnitude of the electrostatic force on Q1 due to Q2. And so there's only one force. They are both of charge plus 33 microcoulombs. And by the way, whoops, this prefix mu right there, that Greek letter that looks like a lowercase u, it's not, it's a mu. That is actually equal to 10 to the minus 6. That's what that prefix means. So that charge is equal to 33 times 10 to the minus 6 coulombs. Right? That's quite a small amount of electric charge. But that's what all three of these particles have. Okay? So with that in mind, let's draw the net force, and I'll draw it in red, on charge 1. If they're both positive, there's a repulsive force. So Q1 would be forced directly upwards along that axis. Okay? And we can draw that as F with the subscript of 1, then 2. And so we write this as the force on particle 1 due to particle 2. Okay? So that's how I will write it from this point onwards. All right? And that's it. In part A, there's only one force. So we want to find the net force on particle 1. Well, there's only one. Keeping it very generally first. You may find that I like to do that, maybe to a fault sometimes. Part A, just looking for the magnitude, not the acceleration, not any equilibrium position, just the magnitude of, well, this force in question, F12. So we can use the Coulomb force, the Coulomb constant K, and then the product of both charges, in this case Q1 and Q2, divided by the distance between them squared, which simply is d. And that's basically it. Now we plug in numbers. So the Coulomb constant, very, very close to 9 times 10 and to the 9. The units are a little bit funky and not very intuitive whatsoever. So don't worry about plugging in SI units or even units at all into your scratch work, right? To reduce what you need to think about and to reduce the characters and the amount of scribbles on your paper, only plug in SI values. If you plug in SI units, be it meters, coulombs, newtons, whatever, if you plug in numbers in SI units, you'll get SI units out, right? Units in equals units out. So you might as well convert everything to SI units before you plug it into your equation, and you won't need to worry about units. So thus, I'll only plug in numbers when I'm doing math, okay? So that's the Coulomb constant, K. The charge Q1 and Q2 is 33 microcoulombs, 10 to the minus 6. I'm not going to write that twice. I'm just going to shorthand it and say squared, divided by the distance d squared, which was 2.8. There we go. And doing math in my head, in other words, consulting my notes, we should get 1.25, if I did the numbers and the math correct. A magnitude, rather, of 1.25 newtons. Again, SI units, right? One quick thing. It's a minor thing, but it's an important thing. Notice in the equation up here, I wrote this in a vector form, right? There's the vector bar on top. However, down here, there's no unit vector to denote orientation. So in our diagram, since it's going up, by convention, let's just call that the y direction, and the unit vector that's associated with the y direction by convention is j hat. So let's just stick that there, plus j, and the magnitude is our answer, 1.25. Okay. Now, on to part B. Part B is a little more tricky. We introduce a third particle, particle 3, aptly named. All right, so let's draw another diagram for 3. 1, 2, forms an equilateral triangle, close enough. Oops, that was 2. This was 1, and Q3, whoops, is, I'll draw it right there. Hopefully that'll be good. All right, just to help us visualize the triangle, I'll draw some dots in between. Since it's an equilateral triangle, the distances in between each particle is still d, and the magnitude of charge 3 is still the 33 microcoulombs. All right, so in part B, what's the magnitude of the electrostatic force on Q1 due to Q2 and Q3? Okay, so we want to find the magnitude now on this Q1 charge, okay, right here. So equal charges, equal distances, even though actually it might not look like it in my drawing. What I will do, maybe to make this a little more visually pleasing, is I'm going to rotate this. Okay, I'm going to rotate this clockwise. Here, you'll see what I mean. I might not have room up there. Let's draw it. Well, tell you what, if I rotate that clockwise, I can just change the charges. Let's do that. 3, 2, 1. All right, the positions won't change, but we can just change what we call them, 1, 2, 3. Okay. All right. So we want to find the net force. There are 2 forces on charge 1 because there are 2 other charges, Q2 and Q3. So let's draw those force vectors. So the force from Q2 onto Q1 will force it along that axis, that direction, right? Actually, let me write that a little bit larger. There. So this is F on charge 1 due to charge 2, okay? The other one is force on 1 due to charge 3, like that. Those 2 vectors I've written in red are of equal magnitude because charges 2 and 3 are of equal magnitude themselves, right? So let's see here. I got black. There we go. Good to go. So let's write out the general vector equation. First, the net force on particle 1. We have as such, well, it's the force on 1 due to 2 plus the force on 1 due to 3. Okay, and like in part A, we're not worried about the acceleration, so I won't draw equals ma. We're just worried about this net force. Okay? Now, again, I like to keep things in variable format and then plug in numbers at the end. Okay, That's how I've been taught. That's how I've always done things. You can try it, and if that works for you, by all means, continue to do it. If it doesn't quite work for you, sorry. Try and follow my work, and then I'll plug in numbers at the very end, okay? If you have any questions, feel free to leave me a message, of course, okay? So we need to break this up into X and Y, right? Because the net force is only in one direction. In terms of these red vectors, we're basically adding them head to tail. So I'm going to translate, say, this vector here down and then go off of the head of vector F12. So it should look something like this. Something like that. And then I'll translate the other one up like there. Okay. And so the resultant should be right there in the middle. This is F1 net. And if you are a little clever, maybe you can guess what it actually is, right? Or would be. But just for completion's sake, let's write out the math. So in the X direction, F1 X, what do we got? In the X direction, well, we need to define X and Y. So let's say that's X and that's Y. There we go. Before we write out the equations, what do we need? We need vectors. So in one F12, the X component, whoops, there we go. The X component of F12, now I need my marker, is actually right there, F12X, and the Y component of F12 is downwards. And similarly for F13. So I'll do Y first. There. Let's move that a little bit out of the way. There we go. And so now that we have the vectors broken up into their components, we can add them up like normal. In the X direction for F12, we have F12X I hat plus, oops, F13X also in the I hat because they're both pointing to the right, okay? F1Y net is the next one. We have F12Y in the J hat. That should be actually negative J hat, correct? So I'll write that as a minus. That's negative because, again, F12 is going downwards, right there. Plus F13Y, which is going up, so that's plus J. Okay. All right. Now we can plug in some numbers towards the end. All right, so we have for F12X in the Coulomb electrostatic formula, we have K times Q1, Q2, divided by the distance between 1 and 2 squared. Well, that's just D, right? And to turn this into the X direction, we have to multiply by a cosine, a theta, right? Look up here what I'm going to do. Right, if I split that angle in half, and I draw the angle theta right there, right? That's also the angle theta directly below it. For f12x, right here, that's the adjacent, right there. What's that cosine theta? What's that value for theta? Theta's right there. Well, remembering that's an equilateral triangle over here, the easiest way to get the angle value for theta is, well, the sum of all interior angles is 180. If it's equilateral, every angle here is 60, and divide that by 2 gives us 30. And so thus this angle here is 30 degrees. And we should have all values we need to calculate for the net forces. Okay? So for right now, I'll leave this in terms of variables, right? For one more line. Then f13x, we have q1, q3, divided by the distance d, like before, times cosine theta I hat. Okay. And, all right, so the Coulomb constant, 9 times 10 to the 9. The charges, they're all equal. So again, 33 times 10 to the minus 6. I'm going to square it for a little bit of shorthand, just in case I run out of room. The distance, 2.8 squared, and then cosine of 30. Now, question, isn't this second term the exact same number? K is the same, the charges are equal, the distance is the same because it's an equilateral triangle, and the angle theta is the same. So just take all that times 2. I guess I don't need brackets, whatever. Times 2. If you do all that, you should get, consulting my notes, 2.17. Whoops, that's definitely not a 2. It should be definitely a 7. There. It's just multiplied by 2, but that should make sense based upon the translation of what we did above, right? Adding vectors head to tail. It's simply twice the addition of the x component. 1, 2. The y direction, well, that's just f13y plus a negative f12y, same magnitude, opposite sign, x, whoops, I don't know what I'm doing, 1y net equals 0. And so our answer is this 2.17. The y directions cancel, right? So this was a problem practicing finding the net force on particles of various charge configurations, right? We had to knock down some cobwebs of vectors from physics 4A, but with a little practice, I'm sure you guys will be fine, okay? Thanks for watching.